Okay, let's begin our new unit on trigonometric ratios. So all about trigonometry, working with triangles, solving for unknown sides, as well as angles. To start things off, we're going to look at something in trigonometry called special angles. So we're going to be working with these so-called special angles or special triangles. Before we get to that, let's begin by refreshing our memory. Let's start with right angle triangles because today's lesson is all about right angle triangles only. So if I have a right angle triangle, by the way, right angle triangle means a triangle with a 90-degree angle in it. If I were to label this triangle with the appropriate terminology, so let's say this was my reference angle right here, and I'll call it theta. Theta is just a Greek letter that we use to represent a number, okay? Just in the way that we use x to represent letters in algebra. Theta is another letter we can use to represent numbers, and again, it's just representing, it's just from the Greek alphabet. So let's call this our reference angle. All right, and so if this is our reference angle here, that makes this side here our opposite side from that reference angle, okay? This side here is known as the adjacent side to the reference angle. And then the longest side of your right angle triangle is known as your hypotenuse. All right, and then we, in the past, we've gone over the formulas for the trig ratios, are sine, cosine, and tangent formulas that help us find unknown sides and angles to a right angle triangle. And so if we can recall that the sine of an angle is equal to the opposite side divided by the hypotenuse. All right, and so, when you see the word sine, it's just a word that represents the ratio of the opposite to the hypotenuse. That's all that word really has in terms of its meaning. Just think of opposite over hypotenuse when you think of sine. So it's just a word that's describing that ratio, that's calling that ratio something. All right. Cos of an angle, or cos of theta, is equal to the adjacent side over hypotenuse. And tan theta is equal to the opposite side over the adjacent side. All right, so that's one set of formulas that we have for our right angle triangles. So we have this knowledge that, let's say, for example, the angle is 30 degrees. So we're trying to find the sine of 30. What that means is that we're trying to find, for a 30-degree angle of reference, we're trying to find what the ratio of the opposite to the hypotenuse sides are. All right, that's all that's saying. When we say the sine of 30, we're just trying to find what the ratio is for a 30-degree reference angle for the opposite to the hypotenuse. Okay, so the ratio. And then another formula that we use in right angle triangles is, of course, our Pythagorean theorem, okay, which applies only to right angle triangles. And what it says is that c squared is equal to a squared plus b squared, or the hypotenuse. Your c always needs to be your hypotenuse. Now, I suppose you can call it any letter you want, but we usually call it c almost always. That has to be your hypotenuse. The legs of your triangle are interchangeable. Okay, these represent the legs, so you can put those in any order that you want, as long as your c is your hypotenuse value. So if the triangle has c given to you, you need to sub it into the left side of the equation. Or if you need to find c, or you need to find the hypotenuse, it needs to be in this format here. Okay, so starting with this idea, now that we've recapped that, starting with this idea of special angles and special triangles were invented by the Egyptians right around 3000 BC, where they didn't have any knowledge of angles. They didn't have any knowledge of equations or variables. There was no knowledge available at that time. But what they did do was they worked with ratios. All right. And so what they found using rope lengths, all right, using rope lengths, what they found. So suppose they use rope lengths of what they would consider 1 unit. What they found was that when they attached 3 units on one side of their triangle and then attached 4 units on the other side of the triangle, the resulting hypotenuse or angled line ended up being 5 units. Okay, and they had their own unit system, right? So they had their own unit system on what they considered one length of something. They had their own unit system. It wasn't 1 meter, for example, it was something else, but they had a unit system. And so what they realized is that when they created 2 legs going with 3 units on one side, 4 units on the other, it created this 5-unit hypotenuse. And what they realized is that it always created a perfectly right angle triangle. Okay, and then from there, what helped them build even the pyramids was just using the idea of ratios or similar triangles. So for example, suppose they knew this to be true, that this would create a 90-degree angle. Well, suppose that they wanted the pyramid to be, I'll use an easy number. Let's use 30 units going across. So they wanted it to be much bigger, right? So they wanted it to be 30 units across, okay? They wanted to create a 90-degree angle here, which means that they would have made a 40-unit line upwards, and then the resultant here would be our 50 units. Okay, so essentially what they did was, what they realized was, okay, if we multiply this by 10, then to keep a similar triangle, we need to multiply everything by 10, and we can create the exact same proportions, just at a larger scale. So that's what they came up with. Now, of course, your pyramids look like this, but they would have built and would have figured out at what angle to do this at based on the right angle triangle, almost like the cross section of the pyramid. They would have based it on this. Okay, so what we're going to be looking at, and I'll erase this just to kind of give myself more space here. What we're going to be looking at is this idea of these special triangles that have been used historically. Okay, and we're going to use what's known as exact values, meaning we're not going to be using actually our calculators. We're going to be taking it back as if, we were in 3000 BC essentially, and looking at almost creating similar triangles, but also memorizing our base unit special triangles. And I'll explain what that is as our lesson progresses. All right, so the exact values of the primary trig ratios for 30, 45, and 60-degree angles. So here's our special angles right here. This is what a lot historically has been built to. Things have been built using 30-degree angles, 45, and 60. All right, and of course 90 is another one. So these angles can be found using the appropriate ratios of sides in an isosceles right triangle and a half equilateral triangle with right angles. These are often referred to as special triangles. So let's look at what's known as our first special triangle, and that is a right angle triangle with 45 degrees as both angles inside the triangle. Okay? And so what you find is that if you were to create this type of triangle with these specific angles, okay, and I'm going to use its most simple units, okay, but I can really use anything. I'm going to say that this is 1 unit here. And if this is 1 unit, because this is a 45 degree in 2 spots here, this would also be 1 unit. Okay? And from there, if you were to do a little Pythagorean theorem, you would find that this would be the square root of 2 units. okay? So here's our first special triangle, right, where we have a 90, 45, 45 triangle. All right, so what we're going to do now is figure out the exact value of the following. So sine of 45 degrees. What that means, okay, sine of 45 degrees is what is the ratio of opposite over hypotenuse for a 45-degree right angle triangle. Okay, so if we go, let's pick a 45-degree angle. Let's pick this one. This is our angle of reference. Our opposite side would be here. Our hypotenuse side would be here. And this would be our adjacent. And you could pick either 45 degree there because they're both 45, and you'll get the same answer. All right, so if we were to do opposite, remember sine is opposite over hypotenuse. If we were to do opposite over hypotenuse, we would get 1, right? Here's our opposite side. It's 1 unit long, divided by the square root of 2. Our hypotenuse is square root of 2. Okay, so I'm going to leave it as 1 over square root of 2, although mathematically we don't leave radicals in the denominator. But for now, I'm just trying to teach this one concept, and I'll get to dealing with that another day in another lesson. All right? So cos 45, which is, of course, adjacent over hypotenuse. So adjacent over hypotenuse is once again 1 over the square root of 2. Okay? So we get the same answer. And you could try this on your calculator. Try in your calculator. Make sure your mode on your calculator is in degree. Okay? Try finding the sine of 45 degrees. Okay? You will get the exact same answer as the cosine of 45 degrees. Okay, so try that on your calculator, and what do you get? Okay, you get something like 0.71. Let's round it to 0.71. And you get the same thing for cos 45. And here you can see why you get the same thing is because where that comes from is that the ratio at its most simple, using its most simple units of 1, 1, and square root of 2, in its most simple way, these two ratios end up being equal. So opposite over hypotenuse ends up being the same as the adjacent over the hypotenuse, which is 1 over square root of 2, which equals 0.71, by the way. If you did 1 divided by square root of 2, you would get 0.71 as well. Okay, so next, let's do opposite over adjacent. So my opposite side here is 1. My adjacent side is also 1. So tan of 45, and you can try this on your calculator, pressing tan 45, you'll get 1. And why is that? Because at a 45-degree reference angle, the ratio of opposite to adjacent side lengths of a right angle triangle is 1 to 1. They're the same value for a 45-degree angle. Okay? So that's one special triangle that you do need to memorize what this triangle looks like, the 1, 1 square root 2, okay? And the other one that you have to memorize is here. It's our 30 and 60 degree angle, 30, 60, 90 degree angle. And the way it gets derived, okay, is we only look at half of this triangle here. So let's say, for example, we took a... let's say, for example, we took an equilateral triangle, which is what we have here. Assume that this is an equilateral triangle, okay? And we were to split that in half. What we would get as our angles, by the way, if this were an equilateral triangle, each angle would be 60, has to be 60, each angle, okay? But because we're splitting this in half, well, now that 60 that was here now becomes 2 different 30s, right? Or just one. I'm only going to focus on one side. So it's just going to become a 30 on one side. And so what I'm going to have is what's known as a 30, 60, 90 degree angle triangle. Okay, and that's what we're going to focus on, is just the 1/2 of this. So the values for a special triangle that is 30, 60, 90, okay, the values for them is opposite of the 30 is the smallest side, which is going to be 1. So let's call this a 1 here. If this is 1, okay, the next biggest side will be opposite the 60. Here we would have the square root of 3. So this line here is the square root of 3. And remember, this is exact values, meaning no decimals. We're going to be using square roots as opposed to writing out decimals that are inaccurate. This is called exact values. Opposite of the 90 is going to be our largest side, which is 2. Now, a lot of people get confused. They're like, isn't the square root of 3 bigger than 2? It's not. Try doing square root of 3 on your calculator. It's smaller than 2. The largest side should be our hypotenuse, which is 2. And so here we have our second special triangle. All right, here's our second special triangle that you will have to memorize. And so now let's write out the ratios for the following. The sine of 60. So remember, sine is opposite over hypotenuse. So let's do that. Let's go opposite, square root of 3, divided by hypotenuse, which is 2. There's our ratio. And so what that means is if you punch in sine of 60 in your calculator, you will get the same thing as square root of 3 divided by 2. Okay? It means the exact same thing. All right, next, and let me just erase those circles there so I can do new ones. Let's go the adjacent over hypotenuse. Well, what's my adjacent side? If 60 is my angle of reference, this is my adjacent side. By the way, this is my opposite side, and this is my hypotenuse. Okay? So adjacent divided by hypotenuse is 1 over 2. And try it in your calculator. The cos of 60 is 0.5. And so what that means is that the ratio of the adjacent to the hypotenuse is 1/2. Or the adjacent is 1/2 the size of the hypotenuse for a 60-degree angle, right angle triangle. Okay? Tan of 60, opposite over adjacent. And again, let me erase these circles. Opposite is square root of 3 divided by adjacent, which is 1. Okay? And so there you have our 3 ratios here. Okay, our 3 ratios. So we have square root of 3 divided by 2 for sine 60. Cos 60 is 1 divided by 2. And tan 60 is the square root of 3 divided by 1. Okay. So you don't have to memorize these actual ratios themselves, but memorizing the special triangle, okay, if we can memorize just that, then we never have to memorize the ratios themselves because we can always derive those ratios if we understand our special triangles, okay? So don't feel like you have to memorize the ratios. Okay, now, let's do our reference angle being the 30 degree. So a 30 degree reference angle. So I'm going to erase everything I have right now besides my side lengths. Because now my reference angle is 30. Which means that my opposite side, sorry, this is a 1 still. My opposite side now becomes this side. My adjacent side now becomes this side. And my hypotenuse stays the same. It's always the longest side. So depending on your angle of reference, the way you label the triangle, of course, will be different. So let's find the sine of 30 degrees. Remember, it's opposite over hypotenuse, which is 1 over 2. And you can try that on your calculator. Sine of 30 is 0.5. Cos of 30, adjacent over hypotenuse, which is the square root of 3 divided by 2. And tan of 30, opposite over adjacent, okay, is 1 divided by the square root of 3. Now again, this isn't proper to leave a radical in the denominator, but I'm not going to worry too much about it in this lesson. Just leave it as 1 divided by the square root of 3. Okay? As a summary, let's fill in the following. We've already done them all up above. We've done 30, 45, and 60, but I mean, there's more special, I guess you can call them special triangles or special angles of 0 degrees and 90 degrees as well. Now, I'm not going to go into just yet the math behind why, for example, the sine of 0 equals 0. I'm not going to go into that math just yet. I'll do that in our next lesson when we do the unit circle. But for now, just in your calculator, if you write or type in the sine of 0, right, you should get 0. So let's fill in this table. Sine of 30 is 1/2. Sine of 45 is 1 over square root 2. Sine of 60 is square root of 3 divided by 2. And then the sine of 90, again, I'm not going to get into the math as to why this equals 1, but punch this into your calculator, you'll get 1. And when we do the unit circle in our next lesson, I'll attempt to explain that a little bit more as to why the sine of 90 equals 1. Okay, cos of 0. Try doing cosine of 0 degrees, and you actually get 1. Cos of 30 is square root of 3 divided by 2. Cos of 45 is 1 over square root of 2. Cos of 60 is 1 over 2. And the cos of 90, just type in cos 90 on your calculator, you get 0. And again, I will explain this in a later lesson as to why it equals 0. Tan of theta. So let's start with tan of 0. So let's try that on our calculator. Tan of 0 is 0. Tan of 30 is 1 over square root 3. Tan of 45 is 1. Tan of 60 is the square root of 3 divided by 1. And then in your calculator, type in the tan of 90, and you actually get, it does not exist. It's actually known as what's called undefined. It does not exist. So you cannot do the tangent of 90 degrees. And again, this may seem really foreign to you, but I will explain when we discuss the unit circle in our next lesson. Okay, so big thing that you need to take away from this is this section, which we developed above, okay, using our special triangles. Those other sections there are 0 and 90 degrees. We will certainly have more conversations about that throughout the unit. So let's see just how well, so let's practice how well we understand these special triangles by completing the following examples. It says determine the exact value meaning no decimals. We can't just sub this into our calculator and get decimals here. We're going to have to use exact values using the ratios we found above to find the value of each expression. So sine of 45, so we have a 45 degree, we have 30 and 60. So we have both special triangles here. I'm going to draw my 45 degree angle first. Then I'll draw my 60. I can draw that a little bit more accurate. Okay, so call this 60, this 30. And our side lengths are 1, square root 3, 2. So those two you've got to memorize, right? So you've got to do your best to practice this as much as you can in order to remember those two triangles. And now what we do is we replace sine 45 with the ratio that it equals from our special triangle. So let's write equals. What is the ratio for sine 45? Well, let's go to our 45 degree angle triangle. This is our opposite side. This is our adjacent side. This is our hypotenuse. Remember that sine is opposite over hypotenuse. 1 over square root 2. Okay? So they're equal to each other. Sine 45, the same as 1 divided by square root 2. But with 1 divided by square root 2, we keep everything as exact values as a ratio. Cos 45 is adjacent over hypotenuse. Also 1 divided by the square root of 2. Plus the sine of 30. So 30 is our reference angle. That makes this our opposite, this our adjacent, this our hypotenuse. Opposite over hypotenuse for sine is 1 over 2. And the sine of 60. Okay, so be careful here now. Now, the 30 is no longer our angle of reference. Okay? It's now our 60 because we have sine of 60. 60 is our angle of reference. So we have to relabel our triangle. This now becomes our opposite. This becomes our adjacent. This becomes our hypotenuse. Or it actually always was the hypotenuse. Sine of 60, well, that's opposite. I'm looking for the ratio of opposite over hypotenuse. Square root of 3 divided by 2. And now we're going to multiply and add these together. So we're going to do numerator times numerator. 1 times 1 is 1. The square root of 2 times the square root of 2. Okay? Square root of 2 times the square root of 2. Well, I can tell you that that just equals 2. But where does the math come from? Right? And I'm going to teach you right now. I'll refresh your memory where it comes from. Remember that the square root of 2 is the same as 2 to the 1/2. So if you had 2 to the power of a half times 2 to the power of a half, you're multiplying the same base, correct? And when you multiply the same base, what can you do to the exponents? Add them. Oops. So you end up getting 2 to the power of 1, which is just 2. So try to memorize that, right? Square root of 2 times square root of 2 is always just 2, because this is going to pop up quite a few times. So that's 2. Plus 1 times the square root of 3 is square root 3. 2 times 2 is 4. Find a common denominator, which is 4. The second fraction stays the same. Here we had to multiply by 2 to get 4. Whatever you do to the denominator, do to the numerator. So we get 2 over 4. So we get, here's our final answer. 2 plus the square root of 3 all divided by 4. Okay, we are not writing out any decimals. No decimals. Do not figure out what the square root of 3 is equal to. Okay, just 2 plus square root of 3 divided by 4. Okay, let's keep doing some more examples. Okay, these are going to get a little bit more challenging. So now tan squared of 60. Now I'm going to save some time here because we've already found, we already know these ratios because we wrote them above. So I'm going to save some time now that you know how to find them yourself. And I'm just going to write out what the ratios are. And so don't be thrown off, first off, by these squares. Just square your ratio. So I'll show you what that means. So find the tan of 60. Find the ratio for it. Square root of 3 over 1. And simply square it. So the tan squared of 60 degrees is the same as the square root of 3 squared. Okay? Plus sine of 30 squared. So let's find sine of 30. We have 1 over 2. Square it. Okay, and now let's solve what this ends up being. So we have the square root of 3 all squared Well, what ends up happening? Square root of 3 squared. Square root and squared end up canceling each other out, and you just get 3. Right? Now, we don't got to worry about this 1 because 1 squared is still just 1. So I don't need to write 3 over 1. I can just write 3, make this easier on myself. Plus 1/2 squared becomes what? 1 squared over 2 squared, which is 1 over 4. Okay, find a common denominator. Remember, this is over 1. So common denominator will be 4. Okay, we multiplied this by 4 to get 4, so do that to the numerator as well. And your final answer is 13 over 4. That's the exact value. No decimals, it's a fraction, it's a ratio. Exact values, that's what we're doing here, not doing decimals. Okay, next type of situation you could see is what if it says 1 minus tan 45? Well, no problem. Let's just follow our rules here. So tan of 45, you go to your 45-degree angle triangle. Tan is opposite over adjacent. So 1 over 1, opposite over adjacent. So what you're going to do is go 1 minus tan 45 is equal to 1 over 1. Well, look what's going to happen there. You're going to end up getting 1 minus 1, which is 0. So that works out pretty easy for us. But let's find the sine of 30. So go to our 30-degree angle. And it's opposite over hypotenuse for sine. So opposite 1 over hypotenuse 2. Minus 2 times sine of 45, well, we did that in the previous two questions ago. Sine of 45 is 1 over square root of 2. So now what we need to do is just really use our knowledge of multiplying fractions, multiplying whole numbers times fractions, and then simplify. So we end up getting 0 times a half here. I know that's going to be 0. Minus. How do you do 2 times or a whole number times a fraction? Well, remember that this whole number is really just over 1. So you really just do 2 times 1, which is 2. 1 times square root of 2, which is 2. So this ends up equaling negative 2 over square root 2. Now, once again, it's not proper to leave a square root or a radical in the denominator, but I'm not going to focus on that right now. Okay, and now our last question of this type is with these numbers in front, right? These coefficients. And all they mean is take your ratio and multiply it by 2. Take this ratio, multiply it by 3. Take this ratio, multiply that by 3. So nothing difficult here, but I wanted to show you an example like this so that you can see it. So let's find the sine of 30. Sine of 30. Again, you can either use this table, but I mean, you're going to have to really know. I mean, you could constantly reference the table, but it'd be good if you can just memorize the special triangles and do this yourself. So sine of 30 is 1/2. So 2 times a half. Plus 3 times cos of 60, also a half, minus 3 times tan 45. Tan 45 is, that's easy, it's just equal to 1. Or 1 over 1, but we can just write 1. Okay, so now let's multiply whole numbers times these fractions. So 2 times a half is 2 over 2, plus 3 over 2, minus 3, right? Bring down the minus sign. 3 times 1 is 3. Now, I understand that 3 over 2 is just 1.5, but I don't want to show decimals. I need to figure this out as one fraction, as an exact value. So my common denominator for all three here is going to be 2. Okay? So this is over 1, this is over 1. So we multiplied this by 2, so we do that same to the numerator. Here we multiplied by 2, so we do the same to the numerator. And now we can figure this out. So it's 2 plus 3, which is 5, minus 6 is negative 1 over 2, or negative 1/2. Okay, let's do a fairly easy example now, a word problem. Suppose a ladder is inclined at an angle of 60 degrees against a wall. If the foot of the ladder is 6 meters from the wall, determine the exact length of the ladder. Okay, so again, a ladder is inclined at an angle of 60 degrees against a wall. So here's our wall, and at 60 degrees, let's say this here is 60 degrees. Okay, if the foot of the ladder is 6 meters from the wall, and I suppose you can interpret this two different ways, this question. Is the 60 here, or is the 60 here? Okay. If it says a ladder is inclined at an angle of 60 degrees against a wall, I mean, I think maybe it's best if we assume that the 60 degrees is actually, this right here. Okay? It's against the wall 60 degrees. Now, it says if the foot of the ladder is 6 meters from the wall, determine the exact length of the ladder. Okay, so, I mean, it's safe to say we have a special triangle here, right? If this is 60, then this obviously is 90. It's against a wall, which means that all three angles in a triangle have to add to 180. So if you have 60, 90, the remaining angle has to be 30. And so we have a special triangle here. Okay. However, we have a scaled up version of that special triangle where instead of this being a square root 3, it's actually a 6. Okay. And instead of this being a 1, right? Normally this is 1 across from the 30. Well, it's a scaled up version. So I don't know what this number is right now. And normally this is a 2. But again, it's a scaled up version. So I don't know what that is right now. But if I can draw my special triangle, I can use my knowledge of similar triangles okay, where if I know that this is supposed to be 1, this is supposed to be square root 3, this is supposed to be 2, I can ask myself, okay, well, to answer the question, it says determine the exact length of the ladder. So I'm finding out what this equals. Well, ask yourself this. If you went from square root of 3 to 6, what did you multiply by to go from the square root of 3 to 6? Okay? Whatever you figure out that to be is the same number that you multiply by to figure out what your new hypotenuse or the length of the ladder is. And you can set up ratios to do that. So let's set up proportions. Let's go, if the square root of 3 now became 6 meters, okay, that proportion should equal to 2. So now from my hypotenuse here is 2 to an unknown. I need to solve for x. This is how you set up these proportions, right? We went 3 to 6, then 2 to x. So cross multiply, you get 12 equals x times the square root of 3. And then x equals 12 divided by the square root of 3. Okay, now I am not, again, we're not focusing, it's not proper for us to have the radical in the denominator. Let's leave it there for now. but our answer is 12 divided by the square root of 3 meters. Just to check our answer, let's see if it makes sense. Okay, so it's saying that our hypotenuse should be, or the length of the ladder should be about 7 meters long, which makes sense. It should be the longest side. Okay, so it should be around 7 meters long. So leave your answer like that for now. Okay, and I'll teach you how to remove this radical in a later lesson. So what did we need to take from a question like this? That we can use our knowledge of similar triangles and set up these types of proportions, where from our small triangle to our big triangle, our number goes from square root of 3 to 6, and then from 2 to x, and we can cross multiply to solve x. Okay, last question here. Two cars leave an intersection at the same time. The first car travels 10 kilometers south, and the second car travels 10 kilometers west. So two cars are leaving the same point at the same time. First car travels 10 kilometers south. The second one travels 10 kilometers west. Okay? Determine the exact distance between the two cars. Okay, no problem. This is just a right angle triangle since we traveled straight south and straight west. And because these are both the same numbers, what special triangle has the same numbers in its legs of the triangle? Is it the 30, 60, 90, or is it the 45, 45, 90? Hopefully you guessed that the 45, 45, 90, okay, has side lengths that are equal. So this is the one that we're going to be using. Okay, so the question is determine the exact distance, right? And anytime I see the word exact, I know I've got to use my special triangles. And when I see that 10 and 10 are the legs of my larger triangle, then I'm trying to match that up with one of my special triangles. And the one that matches up with these legs being the same distance, is my 45-degree angle triangle. So I know that these must be 45 degrees. Okay, they have to be. If those two legs of the triangle are the same, those have to be 45 degrees. So now, if I know that this is supposed to be square root of 2, all right, I need to figure out what this is, x. Well, no problem. I went from, let's set up a proportion. I went from 1 to 10. Okay? That ratio should equal the same as going from square root 2, so one hypotenuse to the other, square root 2 to x. Okay? Cross multiply, you get x equals 10 times the square root of 2 kilometers. And that is an exact value, no decimals, exact values. 10 times the square root of 2 is how far apart the cars are. And that makes sense. Clearly, this triangle is 10 times bigger than our unit special triangle, which means that if the hypotenuse here is square root of 2, the hypotenuse here has to be 10 times that, which is 10 times the square root of 2. Okay, and what I did was I used the proportion to do that, right? I said, okay, to go from 1 to 10, 1 divided by 10, that proportion should equal the same as the square root of 2 divided by x, our unknown. Okay, so there's no question that special triangles requires a lot of practice to get the hang of. Watching somebody do it seems easy, but when you go to try it yourself, it's a lot more challenging. So it's imperative that we do as many practice problems as we can and that you get the hang of and even memorize your special triangles.